Hello students, good morning. Today we are going to discuss one more, that is the last in our chapter 1, that is electric field lines. So electric field lines. So, electric field lines. So electric field lines. Electric field lines. So here, generally what happens is this electric field, though we are able to calculate mathematically, but we are not able to see that electric field, isn't it? So what happens is, understanding will become somewhat, uncomfortable for us. Suppose if we are able to see how this electric field is going to exist in the space, then it will be more convenient. We feel more comfortable in studying the electric field, right? That is why Faraday, what he suggested is, electric field line can be shown, means electric field can be represented by lines, maybe straight lines, maybe curved line, that depends upon the type of charge distribution. So based on the type of charge distribution, this electric field line are going to change. So here, this electric field line, one more name is there, that is, sometimes we call it as force lines also. Electric force lines. Electric force lines is also another name. Sometimes we say field line, and sometimes we say the force lines also, right? So here, vaguely means general to understand what is this field line is. Suppose for example, there is isolated positive charge, there is one positive charge, only one positive charge is there, which we say isolated. Then how the electric field line can be drawn for this isolated positive charge? So for that, what we are going to do is, we are going to take one positive test charge. I told you already. Means it is a very small charge. Very small charge. Almost magnitude equal to 0. So that it does not affect the original field of the charge. Otherwise what happens? Every charge will have its own field. But if the size, if the magnitude of that test charge is going to increase, then what happens is, the original field is going to be disturbed and we can't find the original field. That means the field due to this original positive charge. That is why test charge means it is so small, it does not affect the field, electric field due to the original charge. Right? That is the meaning of that test charge. Now, let us take the test charge and keep it at this point. So this is our positive charge plus Q. Now we take the test charge, that is Q naught. Test charge we are taking Q naught, right? So we have taken Q naught now. So what direction this Q naught is going to move? Away from the charge in a straight line, that is along the line joining the two charges. Suppose this is the line joining the two charges, it will move away in this direction only. Now, if I am going to keep here test charge, then it will move like this. If I keep here, then it will move like this. That means, when we take the path followed by the test charge and join all the points along which the test charge is going to move, that line we call it as the field line. That we call it as the field line, right? So now we want to draw the field line for different charges. That is, first we will take one positive charge. We are going to take a positive charge. we'll take one positive charge. First we are going to take the positive charge. So that is plus Q. We are taking plus Q. This is the positive charge we consider. Now, what will be the field line for this? What are the field line for this? The field line for a positive charge or any charge, always they start perpendicular to the surface of the charge. That is the first point. They have to start perpendicular to the surface of the charge. Perpendicular to surface of charge. That means if I am going to take one positive charge, so this is our positive charge, small charge, this is positive. Now, for this, when you start, it has to start perpendicular to the positive charge, right? So the line must be perpendicular to the positive charge, okay? So it is like this, perpendicular to the positive charge. So here we are going to take now, this is the charge, a small charge, positive charge. I want to draw the field line for this. Then it has to start perpendicular to the surface, perpendicular to the surface. Here perpendicular, here also perpendicular, here also perpendicular. So this is also perpendicular. Next here also come perpendicular, this is also perpendicular. This side also perpendicular like this. All direction they should be perpendicular to the surface like this. Perpendicular to the surface. Okay? So like this they should be perpendicular. Everywhere they are perpendicular and they move away from the positive charge. Away from the positive charge. So that is the electric field line for an isolated positive charge. Isolated means only one charge. So for isolated positive charge it will be like this. But suppose if it is a negative charge, so this is isolated positive charge. Isolated positive charge. So isolated positive charge. Isolated positive charge. Positive charge. Similarly, we take isolated negative charge. This is positive charge, no? But we take now a negative charge. We take a negative charge. So this is the negative charge, right? So in that case, this charge is negative and only one charge is there, that is isolated. Now we know the electric field for negative charge is toward the negative charge. Toward the negative charge. Therefore, when we observe, when we draw the field line, the line should be toward the negative charge. So they should be towards the negative charge, like this. The line should be like this, towards negative charge. So here also it is towards negative charge. Here also it is towards negative charge. Here also towards negative charge. Here also towards negative charge. Towards negative charge. Towards negative charge, like this. Everywhere they will be towards the negative charge, like this. So that is electric field line for a negative charge which is alone, that is isolated. Therefore, here this is the isolated negative charge. It is the isolated negative charge. So isolated negative charge. So for isolated negative charge, this will be the field line. So isolated negative charge. Isolated negative charge. Isolated negative charge. So first point, when you draw the field line, number one, the field line should start perpendicular to the surface or should end perpendicular to the surface. And this field line, they start from positive charge and they are going to end at negative charge. Means technically they originate from the positive charge, they terminate at negative charge. That is the first point. Now let us take two positive and negative charge. One positive charge, one negative charge. Then how the field lines will be here. So we will take now one positive charge and one negative charge. We are taking two charges now. So this is, let us say, one positive charge and this is a negative charge. Two charges we have, right? So now let us say this is positive plus Q and this is negative, say minus Q. Now how to draw the field line for the combination of two charges? What is the rule I told you? Field line, they have to start from positive charge. And when you draw the line, when you start, it should be perpendicular to the surface. That is, we say radial. Perpendicular means what, sir? For a sphere, it is along the radius. So radial line we call, radially outwards. So the line, first it will start radially outwards. Suppose if it is in the middle, it will be like this. It will be like this. But when we go this point, first the line want to move away perpendicular. But because of attraction of this negative charge, the line is going to bend and it is going to move in a curved path like this. It will come like this because of this attraction. Similarly here also. It will come like this. Here also. It will come like this. Here also. It will come like this. So they start at positive charge. They start at positive charge and they terminate at negative charge. They terminate at negative charge. So this is for two charges, one positive and one negative. That is, we can say if the charges are equal and they are separated by a small distance, it is a dipole. We can say it is a dipole. So this is the field line for a dipole. Next, rule number 2. When you draw the line, when you draw a field line, rule number 2. If you draw a tangent at any point to the field line. So rule number 1. First the rule number 1 is what? Rules to draw the field lines. Rules to draw field lines. To draw electric field line or electric force lines. These are the rules we have to see now. Rule number 1. First rule I told you already. Rule number 1. Electric field line should originate from positive charge and terminate at negative charge. Field line originate at positive charge and terminate at negative charge. Terminate at negative charge. Terminate at negative charge. This is rule number 1. Negative charge. Right. Next, rule number 2. Second rule. Rule number 2. Second rule. Now, any point on the field line, if we draw a tangent, for example, I am drawing a tangent here at this point. At this point, I am drawing a tangent. So, when I draw a tangent here, see this? I am drawing a tangent here. This is the tangent. The direction of that tangent should indicate the direction of the field at that point. Listen to the point here. At one point on the field line, if we draw a tangent, the direction of the tangent should indicate the direction of the field. That is this one. See this? I have drawn a tangent, and this is the direction of the field now. See? Is correct or not? The field is in this direction only. So at this point it will be in this direction. Therefore, this tangent should indicate the direction of the electric field. So rule number 2, here, second rule, the tangent drawn to the field line or force line, to field line or force line, field line or force line should indicate the direction of electric field, direction of electric field at that point, direction of electric field at that point, electric field at that point, that is rule number 2, right? That is second rule. Next, rule number 3. Rule number 3, the number of lines drawn to a charge must be proportional to magnitude of charge. Means what? Suppose for example, I have 2 charges. This is plus 2 coulomb. This is minus 1 coulomb. They are not equal. So what happens is, if I draw 4 field lines are originating from plus Q, 4 lines if I show like this, 4 lines if I show, how many lines should terminate at minus 1 coulomb? Only 2. Only 2. So remaining will go somewhere, we don't know where they are going to terminate, but I have to show only 2 lines here. So what does it mean? The number of field lines drawn should be proportional to the magnitude of the charge. Proportional to magnitude of the charge. Number proportional to magnitude of charge. So rule number 3, we have, so third rule, here, rule number 3, so third rule we are writing here. Now rule number 3 here, so third rule, rule 3, number of field lines should be proportional to magnitude of charge. Magnitude of charge. Proportional to magnitude of charge. That is rule number 3. Next, rule number 4. Rule number 4. Fourth rule, no field line intersect with each other. No field line should intersect with each other. So that is rule number 4. No two field lines intersect with each other. Intersect with each other. Intersect with each other. Why they should not intersect? What is the reason for that? Assertion reason they will ask in our MSET or JEE main. So they will give one statement, no two electric field line intersect. They will give reason. So you should be able to remember both. Concept you have to understand. Now, what is the condition, why when you draw a field line, just what I told you. Suppose if you draw a tangent at a point, then the tangent indicate the field direction at that point. Now, suppose there are two field lines, they are intersecting with each other. This is field line 1, this is field line 2. They intersect. Then what does it mean? At the point of intersection, you can draw two tangents or not? We can draw two tangents because at the point of intersection, I can draw, this is the point of intersection. So for this, I can draw one tangent. For one line, line 1, I can draw one tangent. Similarly, for line 2, I can draw one more field line. See, here I can show one more field line like this. Here, for this, I can draw one more field line like this. A direction, tangent. That means what? At that point, there are two directions for the field. Is it possible? Can a field have two directions at one point? No, not possible. Point to point it will change, but at one point, a vector can have only one direction. It can't have two directions, isn't it? Therefore, no field line, two field line can intersect. The reason is, at the point of intersection, two tangents can be drawn. For the two intersecting line, that indicate there are two directions for the electric field at that point, which is not possible. So that is our fourth rule. No field line intersect with each other. So they are the rules. They are the rules. So that is the way that they are the rules that you have to follow when you are drawing the field lines. Okay. So now we will take here. So we have drawn for positive charge isolated. Lines are radially outwards. Radially outward. That means perpendicular to the surface. Next, for negative charge isolated, the field lines are radially inwards. Next, for a dipole, the lines start, that is originate at positive charge and terminate at negative charge. And the number of field lines that we draw for a charge must be proportional to the magnitude of the charge. Proportional to the magnitude of the charge. And no two field lines should intersect. So they are the rules when you draw the field lines here. Right. So based on that, now for example, I will tell you one example here. So now let us see here. That example is, they will give like this. They will take one charge. They won't say what is the charge also. They won't say what is the charge. Just they will take the charge. They will take one charge. This one charge. Right. This is another charge. Now, just they will show the field lines. They will show like this. Just carefully observe. So carefully observe the field lines here. Just they will show like this. They will say this is Q1. First charge is Q1. So this is Q1. This is Q2. They will ask you, what is the ratio of charges Q1 to Q2? Ratio of magnitude of charges Q1 by Q2. Sometimes they will put like this also. To say they want only magnitude, not direction, not the sign. Means positive or negative they don't want first. They will ask you only to find the ratio of the magnitude of charges. So how to find? For that we have to count What is the direction of the field first? That direction not necessary now for us because he is asking only magnitude ratio, no. For that, we know number of field line, they should be proportional to magnitude, just I told you now. So how many lines are there here from Q1? 6. Totally there are 6 lines are there. How many lines are terminating at Q2? Only 4. Therefore, this ratio must be equal to how much? 6 divided by 4. 6 divided by 4, that is Q1 by Q2 equal to 3 by 2. 3 by 2. Then they will ask, what is the nature of the charges? Means what is the nature of Q1? What is the nature of Q2? So what is the nature now? For that, what is the rule I told you? Field line, they originate, means they start from the positive charge and they end, that is we say terminate at negative charge. See? From where they are originating now? From this Q1. So Q1 is what? Positive. What is Q2? They are terminating at Q2, therefore it is negative. So nature of charges are Q1 positive, Q1 is positive and Q2 is negative. Q2 is negative. So common question, the last time they asked in our MSET also, and JEE Main also they are asking number of times, right? So that is the use of this field line. Means examination point of view, when questions are asked, this way we can use the concept of the field lines. And they will ask you, identify the field line for a particular charge. Field line for a particular charge, right? So that is about field lines. Now, regarding electric field line, one more very important point, that is differ from magnetic field lines. That is, I told you already, there will be no electric field in the conductor. There will be no electric field inside the conductor, isn't it? I told you, no field line will be there inside the conductor. So if I am going to take one sphere, let us say one sphere I am taking here. This is a sphere, positive. When I draw the field line, I am going to draw, no doubt, radially outwards. Radially outwards. This will be radially outwards. Like this we will draw. Like this we have to show the field line. But that the field line should not close inside the sphere. Means you should not show like this. It should not close. What is the reason? Because in conductor, we know there will be no excess charge. The point I told you already, whenever we give excess charge, that will be on the surface only. So the field will be only from the surface. No electric field inside the surface. In other words, electric field line does not form closed loops. Electric field line does not form a closed loop like this. Very important for us, examination point of view. Electric field line, they do not form closed loops. That is asked 2 years back in JEE Main. They have given 3 positive charges. 3 positive charges. They have given A, B, C, D, 4 options with 4 different field lines. They asked you to identify which is the correct field line diagram. Field line diagram. That means he has given like this. He has taken 3 positive charges at 3 vertices of an equilateral triangle. One charge, another charge, and another charge. At the vertices of an equilateral triangle he has taken. Then, in one of the diagram, he has shown like this. So what happens here? There is repulsion? No. All are positive only, so they will repel each other. Means the field line, they are going to push it away from this. This charge will push away this field line. 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 Similarly here also. That means now we should not draw like this. There is no attraction there. It is repulsion now. Therefore, now what we have to do is, we have to see this. Here, it should be like this. The field line should be like this. So see here, it will start radially. It will start radially, okay, like this. Now it will move away because of repulsion of these two charges. Next. Similarly here also, same, repelled, 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 here also repelled, here also same thing, repelled, here also repelled, repelled here, repulsion here, repulsion here. But one of the diagram, he has put in the center a circle like this. So this cannot be the field line diagram, because electric field line, they do not form a closed loop. And one of the diagram, what he has done is, two charges, he has shown the field away from the charge. But one of the charges, he has shown toward the charge. But for positive charge, it should be away from the charge, it cannot be toward the charge. So that is important point that we have to keep in mind when we are drawing or identifying the field lines, electric field line. So electric field line do not form closed loops. Important point, very important point here. Electric, important note, very important note, important note. So very important here for us, for examination also. Electric field lines, electric field lines, electric field lines, field lines do not form closed loops. Closed loops. What is the explanation for this? Reason for this? Inside a conductor, there will be no electric field. Inside conductor, inside conductor, inside conductor, inside conductor, there will be no electric field. There will be no electric field. No electric field. That is the reason. That is the reason. That will they will ask assertion reasoned question or a statement 1, statement 2, statement 1 true, statement 2 false. That type. When they ask, they will give like this. Electric field lines do not form closed loop. Statement 1. Statement 2. Inside conductor, there will be no electric field. Statement 2. Then they will say, statement 1 is true, statement 2 is true, and statement 2 is the correct explanation of statement 1. That is first A, B bit. Statement 1 correct, statement 2 also true, but statement 2 is not the correct explanation of statement 1. C bit. Statement 1 is true, statement 2 is false. D option. Statement 1 is false, statement 2 is true. That type. Generally common. Nowadays, absent also they are asking. So for that purpose, these points you have to keep in mind. Right? So that is the important point related to our electric field lines. So what are important points here? Number one, most important point, first point, field line, they originate at positive charge radially outward and terminate radially at the negative charge. Number two, the tangent drawn at any point to the field line indicate the direction of electric field at that point. Number three, no two field lines intersect because at the point of intersection there will be two directions for electric field, which is not possible. And the last one, here the number of field lines that are drawn must be proportional to the magnitude of the charge. So they are the point that you have to keep in mind related to this electric field lines. Okay, so that point you have to keep in mind, and you just go through that old question paper, then you can understand how they are asking questions, as I told you already. So there are 2-3 types I told you. They are asking that type of questions on electric field lines. Okay, so that is about importance of this electric field lines. So now here we will take up some problems in this class and next class. This problem you just see, last time they were asked in the exam, that is related to Gauss law. That problem is based on Gauss law they have asked. Already we have done problems on Gauss law, but exam problem 21 is the previous August exam, no? In that they have asked this one. Let's see this problem here. What is the electric flux for the Gaussian surface A, for the Gaussian surface A that encloses the charged particle in free space. The charged particles in free space. So he has given an arbitrary Gaussian surface. So like this, he has taken one Gaussian surface and he has taken one more Gaussian surface inside. One more Gaussian surface inside. Here he has taken one more Gaussian surface inside. Two he has taken. Then what are the charges he is going to see? Plus Q1, that is plus only. Then Q2 and Q3, 3 charges. He has given the values also. Q1 minus Q1 equal to minus 14 nanocoulomb. Next, Q2, small charges, small letters, use small letters. Q2, it is equal to, he has given 78.85. 78.85 nanocoulomb. Next, Q3, it is given minus third one 56 nanocoulomb. 56 nanocoulomb. Right. So, what is our Gauss law? Now see here. This is Gaussian surface A. Gaussian surface A. Next, Gaussian surface B. Gaussian surface B. Gaussian surface B. Right? Now, see the here. So, what is our Gauss law? Electric flux passing through a Gaussian surface phi equal to Q enclosed means net charge inside the Gaussian surface upon epsilon naught, where epsilon naught is absolute permittivity or permittivity of the free space. That is epsilon naught. That value we know. 8.85 into 10 power minus 12. That is the value. Now, what is the Q enclosed here? First let us calculate the Q enclosed. How much? Q1 plus Q2 plus Q3. Q1 plus Q2 plus Q3. Proper sign you have to add. Very important here. So, what is the values? Minus 14. First we are calculating nanocoulomb plus 78.75. Right. Next, minus 56. So, totally how many now? 70 negative and 78.75 positive. Therefore, the net charge is 8.75. I think it has to be given as 8.85, sir. Sorry, 8.85, not 75. This is 8.5. So 8.85. So 8.85 nanocoulomb. But you have to convert it to coulomb. What is 1 nanocoulomb? 10 power minus 9 coulomb. Therefore, that will be equal to, now Q enclosed equal to 8.85 into 10 power minus 9 coulomb. Because 1 nanocoulomb is 10 power minus 9 coulomb. Now let us substitute there. Substitute the values, all the values. So phi equal to, we have 8.85 into 10 power minus 9 divided by 8.85 into 10 power minus 12. 10 power minus 12. Right. 8.85 cancel. 10 power minus 9, 10 power minus 12. So 10 power minus 9 into 10 power plus 12. When it comes to numerator, it will become plus, no? It will become plus. Then what is our value now? It is equal to 10 power 3. But what is the unit? Unit is very important, no? So unit is Newton meter square per coulomb. That is unit of that. Right? So Newton meter square per coulomb. That is, just we are taking both of them only. What is the charge? Coulomb. What is this? Epsilon naught. You know the epsilon naught? No. Suppose if you don't remember, you can take from here. Coulomb law. Coulomb law, what we have? 1 by 4 pi epsilon naught into Q1 Q2 by R square. Then what is the unit of this? Then we bring this side. Coulomb square divided by Newton square meter square. Now, coulomb by that value. So finally we are going to get Newton meter square per coulomb. Right? So that is the problem asked in the recent exam on the Gauss law. Gauss law, he asked this question. Right? So tomorrow we will do some more problems that are asked in the examination, and with that our fields and charges will be completed. Right?